Good morning, everyone. My name is Martijn Marsman from the University of Vienna, and I'm one of the developers of the Vasp code. It's nice to see so many people here, so nice to see the interest. And first off, I of course, as mentioned in introduction, I cannot help you do better science, obviously, right? Then that is up to you, but I hope that I will be able to clear up maybe things that are unclear about our program or help you work with our program more efficiently. So that is something that I would like to achieve. For this, it's always a bit difficult because I never know the general level of expertise that people bring when they come to a workshop. Some people are very experienced users, other people might be complete beginners. So the lectures are sort of structured, the first lectures are really structured around the beginner, right? So that there's not somebody sitting there and that then after 1.5 hours really has no idea what was going on, which obviously is a bit boring maybe for the people that are experienced users, but they will have to endure this. And because it's hard to tailor these lectures to the general audience, I would like you to ask questions. So that would make the whole workshop, for me, a more enjoyable experience, because then I have a feeling whether I'm conveying the information that you're actually interested in, and I hope that in that sense I will get some feedback from your part. So the first lecture is really about the basics, so about density functional theory, about the way we solve the equations that are involved in this. Let's simply start. So I do something about density functional theory, translational invariance and periodic boundary conditions, plane waves as a basis set, and quite a bit about the projector augmented wave method, because that is really at the core of the efficiency of our program, and a bit about electronic minimization. And this lecture should last something like 1.5 hours, but I always talk too long, so we'll see whether I can. And the other part, so that's what we'll do today. We'll do basics, and we'll have the tutorials in connection to this, which for many of you, especially if you have been working with the program with Vasp already for quite a while, the tutorials of today might not be so interesting. I could see that. Then you can obviously start on the material that I envisioned for tomorrow. There's no pressure on you to run these examples that I've prepared, but they are the ones that are most suitable for people that are sort of starting off in this area. Same thing for the last day, we'll talk about some high performance computing issues. So the way the program is structured, the way stuff is parallelized, things that you can do to run efficiently on HPC hardware. There's no magic in that, so it's not something that necessarily takes a very long time to convey, but it is important. And as Zhengji already told, you're working with actually you're sort of a beta test group for me, because you're working with the version that we have been working on that is supposed to run efficiently on the new hardware that NERSC is going to be bringing online pretty soon. So I hope that you will accept occasional crashes of the software. It is still being actively evaluated. And we'll discuss what you would need to do to run efficiently on the next generation hardware that is going to come online. And that will be the third day. Okay, so generally speaking, in our field of computational material science, ab initio computational material science, the thing that we would like to solve is the many-body Schrödinger equation. So that I've put up here. And it's a deceptively simple-looking equation, actually. And for all its simplicity, it is thoroughly unsolvable. So we have here an Hamiltonian working on our many-body wave function, and that equates the energy, the total energy of the system times this wave function. So a kinetic energy part, a local potential, and here the source of all our trouble, and that's the electron interaction. So why is this unsolvable? Well, it's unsolvable on many levels, but for instance, one of the first things that you might imagine is just storing this many-body wave function that essentially depends on all the electronic spatial coordinates. If I would have a wave function as it is depicted here, and I would discretize this on some grid, let's say in a cubic simulation box with 10 by 10 by 10 points, then storing an object of this size for 5 electron already amounts to 10 petabytes of storage space in complex words. So that is completely impossible for anything but the smallest systems. And the solution that we take, the route that has been taken, is to map this many-body object. So this wave function that depends on all the spatial coordinates of the electrons in our system onto a one-electron theory. And that map is depicted here at the bottom. So basically, we would like to cast this object into a group of functions that depends only on one electronic coordinate. So a single function for each electron, and that's where it takes its name, the one-electron theory. And density functional theory is one of these theories. So this map that I was talking about from a many-body object onto one-electron functions. And the ansatz we take in Hohenberg-Kohn-Sham density functional theory is that we can write our many-body wave function as a product of these one-electron states. And in that sense, it's always called an uncorrelated wave function, because if you'd say, well, if these are like the probability distributions for the single electrons, and such an object factors out into a simple product, that would be an uncorrelated probability distribution. Okay, right. So, and Hohenberg and Kohn have shown that the total energy is a functional of the density. So that we do not need this particular complicated object per se, this many-body wave function. It is essentially to know the total energy of a system, it suffices to know the electronic density, which is a much nicer object, obviously, because it depends only on one single spatial coordinate. So, and they're proved, their density functional theory is essentially an existence proof. So they have shown that, that we can write the total energy as a function of the density, and then it consists of a few terms. There's a kinetic energy term that derives from these one electron orbitals. There's a Hartree energy, so electrostatic energy that depends on the density, obviously. There's a density interacting with the ions. That is an energy term, the ions amongst each other. And everything that we do not know about the system, we lump into another energy contribution called exchange correlation. That is also functional of the density. And they have shown in their proof that this exchange correlation functional actually exists. Yeah, so, which is very nice. But takes us only part of the way, obviously, because existence doesn't mean that we know it to exist, but we don't know what it is exactly, right? So the density is computed from the one electron orbitals in a very straightforward way. And here you see this. So much more tractable than storing such an object would be storing these objects. And from Kohn-Sham density functional theory, we know how to compute these one electron orbitals. They're the solution to what looks like a Schrödinger equation, but isn't. It is a Kohn-Sham equation, but it looks very similar. So where we see again kinetic energy, interaction with the nuclei, electrostatics, and well, corresponding to this exchange correlation energy, there's an exchange correlation potential as well. And Hohenberg-Kohn-Sham density functional theory tells us that both these objects exist. So there is a functional for exchange correlation energy that allows us to write the total energy as a function of the density alone, and the corresponding potential exists as well, but we do not know exactly what they are.
What are EZ and UZ? What are EZ and UZ?
Sorry?
The last two terms in the total energy.
Ah, okay, yeah. So this is the interaction of the electronic density with the nuclei, and this is the nuclei amongst each other. Yeah. So these are straightforward electrostatic contributions, like the heart-free energy is as well. So essentially, all quantum mechanics have been packed into these two objects that we know to exist, but we don't know what they are. So, and that is where, so up to this point, actually, everything is completely exact. Yeah, so it's an exact map of the many-body theory onto one-electron theory. So approximations start at this point. Because these exchange correlation functionals, well, we have to assume something for them. And one of the first assumptions made was to model these quantities on the uniform electron gas. Physicists really like this uniform electron gas. It's one of their favorite toy systems. And for this uniform electron gas, the correlation energy and the potential have been calculated by means of Monte Carlo methods for a wide range of densities. And they have then been parameterized to yield functionals for both these quantities. And in the one of the first and most common approximations, in the local density approximation, we simply assume that the actual density in our system locally behaves like a uniform electron gas. But there's many other, so of course afterwards many other functionals have been created that take into account many other information as well. So maybe not only the local density, but also the local gradient in the density for general gradient approximations, or the second derivative of the density with respect to the spatial coordinates in meta-GGAs. Van der Waals functionals, we'll see them come by in the rest of the talks. Okay, so that's a map to one-electron theory starting from many-body theory. That takes us a long way, right? Because, well, we had this object that we can't store. Well, this is something that looks much more tractable, because here we have something to the power of n, and here we have simply n times these functions. Well, one big problem, obviously, is that n is, for any realistic piece of material, n is huge. Yeah, so this is only part of the solution, obviously. This is still not a tractable one. So in come for us translational invariance and periodic boundary conditions. So because if we use translational invariance, right? So we have a block of material with a unit cell that is repeated endlessly along all crystallographic directions, and we know that our wave functions have to obey these periodic boundary conditions that we apply. Well, translational invariance actually applies that this particular relationship holds, where R is one of the lattice vectors of the real space lattice. So we have that is actually a Bloch function. In this form, we call it a Bloch function. And we know that under periodic boundary conditions, our one-electron functions consist of a part that is written U and K here, that is cell periodic, and then there is a complex phase vector with a period that is larger than the dimensions of our unit cell. So we know under periodic boundary conditions that our one-electron functions have to look like this. And this is a strictly cell periodic part. We label these solutions now by two new quantities, where one is called the Bloch vector, that's this complex phase vector, Bloch vector K, and a so-called band index. And this band index is of the order of the number of electrons per unit cell, so that is quite a limited number, right? And the Bloch vector we constrain to lie within the first Brillouin zone of the reciprocal space lattice. And I'll show you what that means for a particular lattice. So this is an FCC lattice, a real space lattice, and connected to this real space lattice there's a reciprocal space lattice, and that is depicted here. So an FCC lattice in real space translates to a BCC lattice in reciprocal space. And these reciprocal space lattice vectors that are shown here, you can compute them out of the real space lattice vector by means of these relations. And the first Brillouin zone is actually this Wigner-Seitz cell, the first Wigner-Seitz cell in reciprocal space. So all our solutions to the one-electron equation will be labeled by a band index that runs from 1 to anything that is sort of the number of electrons per unit cell, and a Bloch vector that is part of this piece of volume in reciprocal space. Okay, so that takes us quite a way, but still not completely there. So one index is already runs over a very limited range, but these Bloch vectors inside of this first Brillouin zone, there's essentially still an endless number of possible Bloch vectors that we could take, right? So our density then, in terms of these functions, our density involves an integration over this first Brillouin zone, computing the density, and a summation over the band index. So that is essentially written here. And the thing is that although there's an unlimited number of Bloch vectors that we could choose in the first Brillouin zone, there's actually no real need to do it, because these orbitals at Bloch vectors that are close together, they are very similar. So the thing is that what solves our problem then in the end is that we can replace this integration of the first Brillouin zone by coarse-grained sampling of this particular volume. So we replace this integration by a weighted sum over a discrete set of points. And then we have sort of arrived at the point where we can actually do something. Because starting from this many-body wave function, for a huge number of electrons, we have now reduced our computational task to computing these one-electron functions for a number of bands that is of the order of the electrons in our unit cell, and at a discrete set of k points in this first Brillouin zone. So we have now sort of cast this in a form that is computationally tractable. Okay. Are there any questions so far? Something completely unclear? Nope. Good. So, how do we mesh these? How do we choose these meshes in the first Brillouin zone? The most common way to do this is to simply assume a regular mesh. So we will discretize along the directions, along the lattice vectors in real space. We'll choose a mesh that is essentially a uniform mesh of n times n times n points, for instance. And this is a recipe that we can follow. This is, well, here it's sort of written for a simple cubic mesh. So this is a 4 times 4 mesh in 2 dimensions here, inside of this first Brillouin zone of a cubic lattice. And we'll do one more trick, and that is that we do not need to compute one-electron functions at all these points, only the symmetry inequivalent ones. So there are symmetry operations of the lattice that relate one-electron orbitals at this point, for instance, to one-electron orbitals at that point. So we'll compute them only for one of them, and that is what is commonly called, so the ones that we have to compute are commonly called the irreducible wedge in our first Brillouin zone. And of course, we'll then have to adjust the integrational weights or these summational weights accordingly. So we'll set up a mesh, a regular mesh, and then reduce it by by means of the symmetry of the lattice and end up with a few points in the so-called irreducible part of the first Brillouin zone. And that, for those points, will actually then solve the Kohn-Sham equations. Yeah?
Explain the ratio. So if you have 3 equivalent points and then 8 total points, 3 over 8.
Yes? Yeah. Yeah, exactly.
So that's the weight.
That is the weight. So if one of the if there's symmetry operations that relate one particular k point to 4 others, then it would count 4 times. Yes, exactly. And one important part, what one shouldn't forget if one does this, so if one reduces the set of one electron equations that one solves and ends up with this, this reduced set of solutions, then afterwards, after constructing the density, that thing has to be symmetrized again. So you have to, so you reduce the number of points the number of Bloch vectors that you would actually use, but you would have to use the same symmetry operations on all the objects that you then afterwards construct. So that is, so the density, if you construct the density by means of this recipe, but now for a limited set of points and symmetry reduced, then this thing here has to be symmetrized. Same thing for all quantities that you derive out of these functions. So if you would compute some tensor, I don't know, some dielectric tensor, for instance, you would have to symmetrize that one as well using the symmetry operations of the lattice. Otherwise, you get complete crap. Yeah. Yeah.
The formula given for U R necessarily includes a point at the origin. Does it have to include the gamma point?
It does not have to include the gamma point, but there are situations. So this one doesn't include the gamma point, for instance. So commonly, what we commonly do is, so you can create a regular even lattice that wouldn't include the gamma point. You might optionally then shift that towards gamma. That is one thing that you can always do. And there's situations where you would have to do it. I think that's even the next slide. No. But it relates to this point that is mentioned here. So this is essentially this recipe that I already spoke about, right? So you extract the irreducible points, calculate the proper weights and things like this. And then we come to your question. So you can essentially have 2 classes of meshes, one centered on gamma and the other ones around gamma. And the bottom ones, the ones centered around gamma, they can, for certain lattices, break the symmetry. And that is well, shown here. So for FCC and HCP, for hexagonal lattices and for FCC lattices, this can occur. So if the gamma point is not included, then this regular lattice that I apply on my hexagonal cell does not have the symmetry of the hexagonal cell. So, and if I then apply the symmetry operations, and that is actually shown here. I think this is even these are the true points actually. So I have here my regular lattice that does not include the gamma point. Now I apply all the symmetry operations, and instead of reducing the number of points that I get in my set, I blow it up. Because symmetry operations will not map this point to another. It will map it to a point in space where there was no Bloch vector before in my lattice. So the thing is that, well, first of all, the bad thing that occurs is that I now end up with a set of Bloch vectors that is larger than what I started with, which was definitely not the point of applying symmetry. The other, and that is even worse, the other thing is that this is not a really nicely uniform lattice. And that is even worse because these kind of integrations that we do here, or these summations, they converge most rapidly with respect to the number of k points if we sample the Brillouin zone, the first Brillouin zone, uniformly. And that is, well, in this case, no longer the case. So not only do I end up with a huge set of Bloch vectors, but with respect to increasing my sampling density, my result doesn't converge as rapidly, so which is truly bad. But we can always take this lattice. So this is about a 3 by 2 lattice or 6 by 4 I can't judge for here. Shift it to gamma, and then symmetry will be conserved. So yes. Yeah. Yeah.
Just a follow-up question. So for lattices that don't include the gamma point, I've read somewhere that sometimes for like larger lattices you have to include even number, and for smaller number you have to include odd numbers. So, or maybe it's the other way around. But why is the recommendation the way it is, and what is the consequence of? Does it affect the calculation of energies and electron density if you don't have the gamma point? Like I've read recommendations like if you're looking at say lattice is larger than 7 by 7, then you have to use odd number. It's better to use odd number than even number, and if you're using.
Okay, that would be new to me. I wouldn't know why that would be the case. So essentially, you would always have to test whether you converge with respect to a number of k points. And if you do this, I wouldn't mix odd and even lattices. This is sort of a rule of thumb. So if I would go from 2 to 4 to 6, for instance, sampling density, or from 1 to 3 to 5. Because the convergence behavior of even and odd lattices tends to differ. So, but it's always what you can do, right? So it's not the question that am I using enough k points to sample? It's more of the question, can I use enough k points to sample if I have a large system, right? The other thing, and that will come to later, is that the larger your system gets, essentially the volume of your reciprocal space cell starts to shrink, right? So that is one of these relationships that I showed you before. So as your simulation box grows, the need to use many k points becomes less, because for an infinite cell, the size of my reciprocal space cell would be essentially 0. So I would need only 1 point, the gamma point. So there's always this balance. And I'll show you some of the things I'll address one of the factors that is relevant to choosing a sampling density later, and that is the range of the interactions in your system. But essentially, you cannot predict this beforehand. You would have to do convergence tests anyway, always, right? Yes?
Can you explain, using these pictures, what is the gamma point?
Ah, sorry, yeah, a 0. So the origin of the cell, yeah, that's the gamma point.
So what will determine whether you can make the reduced cell around or on the gamma point?
It's by choice. So the standard recipe that we take to determine the points in our grid. So either these factors are even or they're odd. If all of them are even, then 0 will not be part of the grid. And if one of the directions is odd, then the gamma point will be, so if the sampling along one of the directions is an odd number of points, then the gamma point will automatically be included. Yeah.
Can you repeat the questions as they're asked, just for the audio and for the...
Okay. Yes. Yes. I will. Yes.
If you select a poor mesh, does Vasp quit, or does it just give you a warning?
So if I select a poor mesh, Vasp does not quit. Actually, there's even warnings that tell you that you have selected a mesh that is not commensurate with the real space cell that you have chosen. And it will still continue. It will even say a warning, this is very bad news, but most of the time the results are still usable. So no, it doesn't, it can't judge. It can't really judge whether the result will be good or bad. Yeah.
Question from online.
Yeah.
Relating to what you were saying earlier, why not always use a gamma-centered K-grid then?
Yes, that is, so why not always use a gamma-centered K-grid? That is a very good question, and actually I always use gamma-centered K-grids. Just don't think about this. There's, having said that, there are situations where sampling is more dictated by what you can do than by what you would like to do, right? So it might be that you, yes. But I would actually advise to use gamma-centered grids. That avoids all these problems, yes. Yeah.
So in real, what really happens from the left figure to the middle? Say, is it that you say you use 5 by 5, you set the grid to be 5 by 5, and then you switch on the symmetry and you get a tensor?
So what actually happens going from here to here? So essentially what destroys so what is the problem here is that rotations by 60 degrees are not symmetry operations of this regular even lattice. So what happens is that I take my cell, or I take this grid, and I rotate everything by 60 degrees around the origin, and then I end up with something like this.
So is this can be accomplished by just a switch on the symmetry?
This is always done as well. By default, symmetry is switched on, so the code will always try to use symmetry when it finds operations. So you can prohibit it, you can tell the code not to use symmetry, but otherwise this is always done.
And this based on using the same behaviors for that.
Yes, this is used basing, well, you in your file, in your k-points file, where you specify the sampling of the reciprocal space. There you say, okay, I want 4 points along this this direction in reciprocal space, and 6 along another, and things like this, right? Then it will set up this grid accordingly, and use all the symmetry operations it has found to try to reduce the number of points in your grid, but it might end up by finding new ones, right? Yeah. Okay, so why not use k-point centered meshes? Yes, that is a very good question. I simply always use them. Gamma centered meshes, yeah. Okay, well, this is just a slide to sort of show you that although we use periodic boundary conditions, well, Vasp is a code that comes out of solid state physics, so they're using periodic boundary conditions is an obvious choice, because our solid state material consists of a unit cell that is repeated infinitely along or essentially infinitely along all directions. But well, although we come from this situation, it doesn't inhibit us try to compute molecules or surfaces. And essentially the trick that we do there is we take a simulation box that is sufficiently large so that our small molecule is surrounded by a lot of vacuum, and these are the periodic images, so the periodically repeated images, and the distance between them has simply to be large enough so that they do not see each other, that they do not interact anymore, and then we assume that we have a molecule, a free molecule in space. Same thing with surfaces. Well, surfaces there, we have, well, this is the surface of some oxide, a surface oxide, and then there's vacuum, and that is the bottom of this slab, periodically repeated. So this has to be large enough so that one surface doesn't see the other one. And another thing is that the number of layers in our slab has to be so large that the electronic behavior in the center is sort of bulk-like. Otherwise, we do not have a true representation of a semi-infinite system. Okay, so yes?
We have a question about reciprocal space.
Yeah.
From the previous slide.
Mm-hmm.
The question is, my mind does not work well in translating the real space to reciprocal space.
Yes.
Can you recommend a software pack to help to visualize these transformations?
Oh.
The resulting distribution of the k-point mesh.
A software pack, I wouldn't know actually. Maybe somebody knows good software with which to represent meshes. But there's only a very limited number of possible Bravais lattices. And there's all kinds of nice PDFs in the you can find on the web that show you the reciprocal space cells related to all the possible Bravais lattices. So because pictures like this, I think I did use some software to generate this picture that was sort of prohibitively complicated to work with, but it's possible to get all this kind of pictures, but there's only a few of them, in fact, a few possible Bravais lattices. Yes, and for the rest, I don't know how much is understanding and how much is getting used to it. At some point you get used to, you see a picture and you say, this is an FCC cell, and you immediately know the shape of the reciprocal space cell. It's not the most important thing maybe. The very important thing to realize is how these sizes relate, how that a huge cell or a large cell in real space corresponds to a small cell in reciprocal space. That's one of the things that is good to know, because that directly translates to the number of K points one would use. Yes.
So when you talked about studying an individual isotopic molecule and surrounding periodic replicas, does it make sense to do a K-point convergence with it, or just consider a gamma point alone?
Actually, yes, that's a very good question. So if you use, if you want to do something like this, so a molecule in free space, you do not want to spend effort describing the interaction between neighbors. So you would use only the gamma point, never anything else, because using a different K point or adding other ones only means that you are trying to get a better description of the interaction between the neighbors. So actually you're worsening your result if you use anything but the K point. Same thing here. So there's for instance this direction, right? So where we have a vacuum. So they're associated with this direction. There's also a reciprocal space vector, and along that particular direction you would never use more than one K point, because otherwise you're just spending computational effort in trying to describe the interaction between the slabs, the things that you exactly want to throw away actually. Yeah, that's a good question.
So another one online. Should we always use the default value of ISIM, or sometimes should we switch it off for a very large cell?
So for a very large cell, you would like to switch it off for a very large cell. There's no real need to switch it off, although if you have a very large cell and you have only one K point, there's also no real need to use symmetry, because it doesn't bring you a lot. But it might help in some cases to still, even in that particular situation, to use the symmetry, because it will reduce noise in some quantities. That's one thing. But there's one other thing, and that is maybe very important to realize, that that using symmetry obviously also dictates, it dictates the symmetry of the solution you will find. So, for instance, consider you have a cubic system, maybe a large surface, and on the surface you would like to, in real life on the surface something like a polaron exists. So two atoms move to each other, and an electron would localize in between them on the surface or on some defect. So that physical situation might break the symmetry of the lattice you started with. So if you would enforce symmetry, you would never find this solution. So in some cases, it pays off to think about what symmetry you start with, because if you give the program a certain symmetry and you enforce it, it will never move away from this. So, and that might actually lead to the fact that you would not find the physical solution. So yes. Where is this important? This is important, for instance, reconstructions on surfaces. They might break the symmetry completely. Where would this conceivably be very important? Magnetic systems. Magnetic systems might have the magnetic subsystem might have a lower symmetry than the underlying crystalline system. So these are things where, and that is something that you could find maybe by switching off symmetry and simply let the program search for the configuration with the lowest total energy. But even that is not always guaranteed, right? Because the program will move to a minimum, that is guaranteed. But whether that is a global minimum, yes, that remains to be seen. Yeah, there's no way to judge this. Yes?
So we have a couple more online questions. One about grids and one about the gamma point. So What's the difference between MP grid and auto grid in Vasp, and which is more reliable?
MP grid and auto.
Which I think is probably going to go to this slide.
I don't think there is a difference. There shouldn't be. So a Moncourse-Pack grid or a gamma-centered one, I don't actually know what the auto grid would be. Maybe it's something we can. I would have to look it up. So all automatic grids are essentially Moncourse-Pack grids. So they might additionally be gamma-centered. If they're odd, they are gamma-centered. It might be that there's another option that is called auto, but that does probably do exactly the same thing. But I could come back to this. So maybe if you could advise people to, if they have these kind of questions, they could send it to me by email. That would probably be better, so that we could do it offline. Yeah? Because here we can obviously talk in the breaks, but for offline people that would be difficult. Okay, so I already see that I probably need 5 days for this workshop. This is the same picture as before, just less nice. Okay, so, well, let's move on. Yeah, we can. If there's any more questions with respect to sampling of reciprocal space, please we'll simply talk about this later or during the hands-on or whatever. Yeah. So this is the total energy expression that we talked about, right? So depending essentially on the density. Well, the kinetic energy, it's the kinetic energy computed from the uncorrelated one electron orbitals, as we say, but those are essentially a functional of the density. So this thing is formally also a functional of the density. So the total energy is truly a functional of the electronic density alone. Kinetic energy is written here. It's straightforwardly computable from our Kohn-Sham orbitals. Hartree energy is simply electrostatic, so we have two charge distributions interacting with a r minus r, with 1 over r, where r is r minus r prime, the distance between 2 points in space. And well, this is the interaction of the electrons with the, well, sorry, this is the density consisting of the electronic density and the nuclei, and the density we compute from our Kohn-Sham orbitals. Basically a repeat of something that we have seen before, and this is the essential thing that we have to solve. Those are these Kohn-Sham equations, right? And they are, as you see here, they're eigenvalue equations. And they depend obviously on their own solution, right? Because our Hamiltonian is basically determined by the electronic density that is determined by the solution of the equation. So this is a self-consistent problem. Right. First thing that we do is, well, we have to make a choice how to express the solutions of our equations. And in solid state physics, well, it was sort of an obvious choice at some point to use plane waves to do this. So we have to express our solutions, and in essence, the cell periodic part of these Bloch functions we have to express in some basis set to be able to work with it. And what we do is essentially Fourier analysis. So we expand all our functions, all cell periodic functions, in terms of plane waves. Right? So, well, that's written here. So this is a plane wave, e to the power of I and a wave vector times r. And these are the expansion coefficients of the cell periodic part of the Bloch function. So this would be the complete Bloch function with the additional Bloch vector in the exponent. And all other cell periodic quantities are expanded in plane waves as well. So our density and the potentials. And we have to make a choice, and this is one of the essential parameters that we have to set in our calculation. So because this, of course, this set of plane waves is again essentially infinite. We could choose any well, if you look at one of these simulation boxes, we could use any sine or cosine that fits in this unit cell. So there's an infinite amount of them. And we decide on which to include in our basis based on this criterion. And this is the kinetic energy associated with a particular plane wave. And what we say, okay, we limit our basis set to those plane waves with a kinetic energy below a certain cutoff energy that you have to choose. Yes. And there's defaults in the program because it depends on the kind of potentials that you use. There's information in those files that gives some hint what kind of cutoff would be sensible. But essentially, this is something that the user, that I advise people to set. This is one thing that you would like to control yourself, at least to be aware of the cutoff that is used. So, and the nice thing now is that and we'll see this later, that there's a bunch of operations that are done, that are nicely done in real space, and there's a bunch of operations that are more conveniently done in reciprocal space. And the nice thing of using plane waves as a basis set for all these quantities is that we have a convenient map between our quantities in real space and the ones in reciprocal space, and that's the fast Fourier transform. Yeah. And when I say convenient, it means that computationally it scales favorably. So a fast Fourier transform scales like n times the logarithm of n, where n is the number of plane waves in your unit cell. Okay. So that is sort of recaptured here. So why did people start out with plane waves? Well, that was historical reasons that we don't have to go into now. Practical reasons is that many of the expressions that we saw before are easy to implement if we are able in terms of plane waves. And computational reason is that we can use these FFTs to efficiently do a lot of the operations that we have to do solving the Kohn-Sham equations, of which computing the action of the Hamiltonian on the orbitals is the key one. And the action, I don't know, I will probably use this term quite a lot. So computing this point-by-point product of this thing, in brackets is our Hamiltonian, point-by-point product of this with the Kohn-Sham orbital, that is called the action of the Hamiltonian onto the orbital. So this is a pictorial of the situation that we have. We have a real space lattice where we choose a number of points. We discretize our real space. In this case, well, it's a cubic lattice, and we have a number of points here, and it's an n by n grid in our real space simulation box. And with this associated is an n by n grid in reciprocal space as well. And for instance, one of these, this sine function along a certain direction in our real space cell corresponds to a certain point in our reciprocal space cell, this reciprocal space grid, connected by fast Fourier transforms. And this is this cutoff energy. This is a pictorial of the cutoff energy that I talked about. We can, of course, we can take this particular criterion here, and we can cast this cutoff energy into the size of a certain vector in our real space cell. So we end up with this area, and all the points inside of this area we consider part of our basis. For the fast Fourier transform, though, we would have to compute contributions at the other points as well, obviously, right? Because we have a direct map of this situation to values at all points on this regular grid, but we store only the ones that are inside of this particular area that corresponds to our energy cutoff. Okay, so that means that, well, this one was cell periodic, part of the basis. another one that is also must be cell-periodic always, another plane wave that is still part of our basis. And at some point, obviously, we'll get higher frequency components that lie outside of the area that we consider part of our basis. Yes?
Can you explain this analogy a little more? You're looking at a two-dimensional space or a one-dimensional space where the other dimension is energy?
No, this is the problem here is this is a two-dimensional space.
Yes.
And this would be an oscillation along one of the
Is
dimensions.
it energy density oscillation?
No. This is the wave function.
Sorry, electron density oscillation.
Actually, this would be this could be the density. Yes. Although negative values would be bad in the density. So let's say that this is an orbital. Yeah. So and both of these directions are actually real space directions. So in that sense, this sign is badly chosen, right? So this is just sort of a hand waving explanation. So you shouldn't associate anything with this particular direction.
Okay.
Yeah. Yes. Yeah. I should do more fancy graphics to do this. Actually, it should be a color-coded plot probably, because you would have a sign traveling along this direction everywhere. So that would be like a sheet. Yes. Yeah. Good point. Yeah. Okay. So this would be a sheet along the other direction, and that is yes. So same thing here. So now we come to because we haven't spoken about this. We have spoken about this criterion, this particular criterion that determines which plane wave components we consider to be part of our basis, but that does not necessarily tell us how many points we need to sample our cell, right? It will only tell us that if we choose a certain number of points along this direction and along this direction and have the same grid in reciprocal space, which points will be part of our basis and which ones won't, but it doesn't tell us how many points to choose, right? Okay, so that is what we come to now. So how dense do these grids have to be? So and essentially what we see here, so if we look at the charge density, and there's a certain area in our reciprocal, if we look at the wave functions, there's a certain area in our reciprocal space where we have components that we consider to be part of the basis, right? So if we do an FFT, we have a certain function in real space, and to compute the density, we would multiply this function essentially by its complex conjugate. Which means that if we have this sort of Gaussian shape here times itself, we'll end up with another Gaussian, but that will be more strongly peaked. Yeah. So in Fourier analysis, that means that the frequency components to describe this one truly, you need higher frequency components. So essentially, if I have here at the boundary a certain sine function or an exponential function with a certain that is a certain frequency contribution to this one, then this one will have contributions with a reciprocal space vector twice the size. Yeah. So consider the size of this particular basis. How large does my grid have to be in reciprocal space? Well, to represent the density, which is a product of these one electron orbitals, I need twice as many points along a certain direction. Right? So that's one thing. And that's if I wouldn't do that, then I would end up with, I would have contributions that are outside of my grid. And in signal theory, that means aliasing. That means that you have contributions with a higher frequency that are picked up at a lower one. So I would start to if I have points, so if my grid is not large enough to include this particular circle, then I will have points at higher frequency that will contaminate my Fourier components at lower frequency. And that's one of the things that you will always see if the program will allow for a certain amount of aliasing. In standard precision, it will allow for for a certain amount of aliasing, and it will write out a warning. But if you want to do a very accurate calculation and you set the precision to accurate, you will essentially end up in this situation. So you have a basis, consists of a bunch of plane waves to represent the orbitals, and the grid will be large enough to essentially incorporate a reciprocal space vector of twice the size of the largest one that is used to represent your orbitals. Is that... I always feel uncomfortable explaining this. So if somebody says, okay, no, I don't understand what you mean, so is any questions here? Yes?
So for this, that means in the real space, okay. So for this, okay, so this is in receptor space, but for example, if you want to truncation the density is sparse, that means always the density is more sparse than wave function, right? In real space.
In real space?
Yeah.
What do you mean by sparse, actually?
That means so the density.
You mean the extent in?
Is more localized.
Well, it's more strongly peaked. And of course, more localized, it looks only more localized in this sense of the example that I've chosen here, right? Because you have completely delocalized electronic states as well. And if you then look at the charge density that arise from a completely delocalized one electron orbital, the density that is associated with it is also delocalized, but it will have features with higher frequency components. That's the way to look at it. So, yeah? Yes?
So how does this relate to K points and the cutoff?
Very good question. So the cutoff determines this area, right? So I say that I want to have basis vectors with. So yes, let's go to this. Oops, sorry. So the distance between these points here is essentially determined by the size of my unit cell. So that is written here. You see here B2. That is the reciprocal space cell. So it's one of the vectors, one of the basis vectors of my reciprocal space cell. Yeah. So if I say, okay, let's start in real space. I say I want to use a 10 by 10 grid in real space. Let's say I start with this. Then in a reciprocal space, I will have vectors that are along this direction are 10 times the size of the reciprocal space basis vector. Yeah, and for my cell periodic part, these G vectors that express the Fourier components of my cell periodic part, they are always integer multiples of my reciprocal space vectors. Yeah, so I choose 10 points in real space. I end up with 10 points in reciprocal space. The distance between them is, well, this is 1 times G, 2 times G, and so on and so forth. So that means that starting from 0 to some point, there's going to be a maximum size G vector that I can incorporate in this lattice. Yes? So the maximum size, with this maximum size, there's a kinetic energy criterion connected. Yeah? So if I can at max have a G vector of this size, that means that I can represent my wave function with respect to this kinetic energy criterion with respect to a certain, let's say 100 eV. If I choose more points in real space, then this will incorporate larger G vectors, which means that I can now represent my wave function with a cutoff energy of, let's say, 200 eV. So by setting this particular kinetic energy criterion, going the other way, right, I sort of start to dictate how many points I need to sample in real space. And how many points do I need to sample? And that is given by the fact that I not only have to be able to represent my one electron orbital, but the associated density. Yeah, so it's all connected, but these distances here between the points in reciprocal space, they're given by the size of my reciprocal space basis vectors. So asking about k points are up to the size of my reciprocal space basis vectors. So G is integer multiples of these basis vectors, and K is chosen such that it goes from 0 up to the size. So essentially K are variations inside of these little boxes. Yes?
So your kinetic energy cutoff is determined by the smallest real space distance or separation you need to deal with, and that is set by the spatial extent of an atomic orbital, or that's set more by the distance between atoms? It has more to do with the sharpness of an orbital than anything else?
Yes, it has to do with, so essentially, the kinetic energy criterion you have to choose. But you have to sort of choose by hand, but obviously it will be associated with the, so essentially you control how many fine features in my orbital can I describe. So if I have a very S-like delocalized orbital, I wouldn't need so many plane waves to describe it. If I go to a system where I have d electrons that are strongly localized, I would need many more Fourier components. So in the end, it is always related, obviously, to the physics, to the orbital that I try to expand.
D orbitals have a larger spatial extent in general, but they change sign more frequently. Which would be important for the cutoff.
So what would be important? That will come to. So features. So these changes of sign. So nodal features near the cores, that will try to get away with this. We try to remove them with this PAW approximation. It's a pseudo-potential approximation that I'll show you later on. Otherwise, we would be dead completely. But essentially, a d electronic orbital doesn't have this, right? So the 3D orbital doesn't have nodal features per se, but it's strongly peaked closer to the nucleus. Mm-hmm. So it would have a lot more Fourier components than a 1s orbital that is spread out much more strongly. Yeah. Yes. So essentially, the kind of cutoff you have to choose depends on the physics. And all the grids are then derived from this particular cutoff in accordance with the considerations that I've tried to outline here. Yep.
So when you mentioned about going with G
Cool.
can you stand up to us? So when you mentioned going from describing the wave functions to the density, you have to go from G cut to 2G cut, right? But you said that introduces aliasing errors.
If the grid would not be large enough to incorporate 2G, then you have aliasing. So if I have a grid that incorporates this sphere, but not this one completely, the one with twice the radius, then I have aliasing. And that is actually the standard behavior of the code. It will allow for a certain measure of aliasing. Because, I mean, aliasing is bad, but the question is how bad is it? And how expensive is it to completely do without? So normal precision allows for a certain measure that was, well, at some point judged to be acceptable. Is it acceptable? That will depend on the thing that you're doing. And mostly, obviously, on the kind of energy differences that you're trying to resolve. If you're comparing two situations and there's like a few millieV of energy difference between them, then probably you wouldn't accept any aliasing. Yeah. So, okay. Good. So, yes. So the action of the Hamiltonian, like I said before, this point-by-point product of this object with the 1 electron orbitals. Yeah, to compute this, it is nice to do some stuff in reciprocal space and some stuff in real space, as I mentioned before. So, for instance, the kinetic energy is easily evaluated in reciprocal space. So this would be this is the representation of our orbital in reciprocal space. Those are essentially these coefficients, right? These Fourier coefficients that we talked about, and the kinetic energy of such an orbital in that particular representation is a simple product of the kinetic energy of the plane wave it consists of with these Fourier components. So that is easily calculated with a computational effort that scales with the number of plane waves. Something like the local potential is more easily calculated in real space, right? So this one, point-by-point product in real space, which is, so we need to be able to shuttle back and forth. We need to be able to represent our orbital in reciprocal and real space. Kinetic energy we do in reciprocal space, local potential we'll do in real space. On the other hand, solving the Poisson equation for the Hartree contribution to the local potential is again better done in reciprocal space. That's mentioned here. So exchange correlation we can do in real space, but for the Hartree potential, where we need to know the potential arising from the electrostatic potential arising from our density, for that it's more easily done in reciprocal space. We transform our density to reciprocal space, and the potential, so the solution of the Poisson equation, is then the simple product of our Fourier components of the density with 1 over g squared. Solving the Poisson equation in real space is far from trivial, but doing it in reciprocal space is actually trivial. So we get our potential in reciprocal space, and then we do another Fourier transformation to get it into real space, and then we have our total local potential in real space and do a point-by-point multiplication. The cost of that is actually scales as the cost of doing these Fourier transforms, and that is n log n, where n is the number of plane waves in our FFT grid. So not in the basis, but in the FFT grid, right? So the number of plane waves in our basis is much smaller than the one in our FFT grid. Yeah. Okay, so the worst scaling part of such an operation is actually n log n. And that is due to the fact that we are able to use these fast Fourier transforms. Yeah. So we might have another look at this situation that we saw before. So the action of our Hamiltonian, in this case the action of the local potential on our orbitals. We can have a quick look at what that means in terms of cutoffs in reciprocal space. So as we said before, we have this large sphere that just about fits inside of our FFT grid in reciprocal space that represents the basis for our density. So from this we get our potential by dividing by g squared at all the points where we have data. And that gives us our local potential. So and essentially what we then do, we take it to real space. So we have some object. This is now our local potential in real space, and we'll multiply it again by our orbital. So again we have a multiplication, which would mean, obviously, that if we had a basis for our orbitals of radius g cut, then this would be 2 times g cut. If we then multiply the potential with an orbital, we would end up with Fourier components up to 3 times g cut, actually, right? So that is what is written here, yeah. And this picture tries to show you why it's not necessary to use an FFT grid that incorporates this whole huge circle. So essentially, what we accept here now is aliasing. We don't increase our grid. So all these all these areas that are outside of our grid fold back into the grid. That is what this aliasing means, right? So all these points here and here and here, they're strongly affected by aliasing in this product. But what we keep, and that is what is basically, if we look at our Cohen-Shum equation, yes, our Cohen-Shum equation tells us that the action of our Hamiltonian is essentially of the nature of an orbital, right? So the action of our Hamiltonian onto the orbital is a scalar times our orbital. So, and that helps us here because the area inside of this that is not affected by aliasing is exactly of the radius of the basis that we use for our orbital. So when we compute this product, and we have all kinds of Fourier components that are strongly contaminated by aliasing, the part of our representation that is unaffected by aliasing is exactly the part that makes up the basis of our orbitals. And h psi equals psi, that's essentially the kind of equation that we solve. So these are the only components that we'll keep after computing the action of the Hamiltonian on the orbital. So that is why the essential grid that we would have to use is actually of the size of 2 times g cut for the orbitals, and not 3 times g cut for the orbitals. You look very skeptical.
And you get the part like 2G, which turns out into the potential, but then it's 3G cut, I didn't get this part at all.
Okay. So 2G arises from the fact that 2 times the G cutoff arises from the fact that we have taken the product of 2 orbitals. Yeah? And now we take this product of 2 orbitals and multiply it with an orbital again. So we go from 2G to 3G. Yeah? And that is the radius of this large circle. Yeah, and this sort of tries, you very hand-wavingly tries to show you that we do not need to choose our FFT grids so large that we actually incorporate this 3 times G cut. It is sufficient to incorporate 2 times G cut. Yeah. Yes. Yeah, and this is called, well, okay, so the product of this times this is sometimes called the residual vector, but we won't go into that, why that is so. Okay. Is that sort of? Good. So, that is all very nice. But the number of plane waves to describe tightly bound states, so strongly localized state, or the rapid oscillations of the wave function near the nucleus would still be prohibitively large, right? So we have this way of representing our orbitals, but in practice, anything beyond lithium or hydrogen, we couldn't represent the orbitals in any tractable number of plane waves. So because if you have, I don't know, you go from 2s to 3s, you get one node close to the nucleus. To keep those states orthogonal to each other, they have to have an additional node, and describing these fine features takes a lot of plane waves. So there's 2 things that are commonly done. There. One is to introduce the frozen core approximation, and that is because if you have an atom with quite a few electrons, there's a whole bunch of them that don't really contribute to the chemical binding, right? They don't notice whether they are a free atom or they're inside some material. They're always the same. So they're not important for the physics or not important for the chemistry of the situation. And we can compute them one time and then compute the density associated with them and keep that frozen. So that's already quite good because that gets rid of these deep-lying states that are generally quite contracted in real space. So they would need a lot of plane waves to represent. So that's one thing. the frozen core approximation. And the other thing is that, that we'll start to use, instead of using the exact potential around the atom, we'll use a pseudo potential around the atom to get rid of these rapid oscillations near the nucleus for the states that we do actually want to calculate, that are not part of this frozen core. Yes, so pseudo-potential methods, there's a whole bunch of them. So starting from norm-conserving pseudo-potentials to one step beyond ultra-soft pseudo-potentials. And I will show you something about the projector-augmented wave method, because that is the flavor of pseudo-potential theory that we actually use in Vasp. So the general idea is, like I said, if we have features around here, so we have an orbital with a few nodal features near the core, then getting this right to express this part of the orbital in plane waves is expensive, and often prohibitively expensive. The thing is, though, that the part of the orbital that we have to get right is the part where, if I put two atoms close together, their orbitals will feel each other. That will happen at some distance away from the nucleus. So if I describe this part of the orbital correctly, let's say the part where chemical bonding occurs, that would be sufficient. So I don't need to represent these nodal features per se. So instead of using the exact potential, I'll use a pseudo potential that at some cutoff radius resembles the true potential exactly. I'll use this potential instead of the true one, and I'll end up with an orbital that is much more well behaved. If I choose this potential wisely, I end up with a pseudo orbital, so no longer the true orbital, but a pseudo orbital that doesn't have these nodal features, but matches the true orbital in the area of chemical bonding where I need to correctly represent it. So that's the general idea of using pseudo potentials. So the PRW method is slightly different, and I'll show you in essence what the essence of that is. So this is these, like I said before, we have true orbitals and pseudo orbitals. So in pseudo potential theory, you would use an effective atom. So if I say, okay, I have an aluminum that normally well, the states that I consider to be part of my valence, so this is frozen core, and then these would be states that I consider part of my valence manifold, so 3p and 3s, that I would need to represent. Using this pseudo-potential theory, I get rid of the nodes, so my effective aluminum atom is of the states that I represent are effectively of 1s and 2p nature. That is sort of depicted here. They are nodeless, but they're not guaranteed to be orthogonal to the core anymore, right? So I chuck this out, and using this effective pseudo-potential, I end up with states that are not necessarily orthogonal to these core states anymore. In the PIW, we do things slightly differently. Implicitly, we'll use, in the formalism, implicitly we'll be working with 3p and 3s states, so not with nodeless ones. We have a way of conserving the nodes and a way of conserving the orthogonality to the core state. So in that sense, it is, and that is what is written here. The PIW, as opposed to conventional pseudo-potential methods, conserves the nodal structure in a certain way without having to represent them in plane waves. That is the essence of the method. So, on the other hand, this picture does actually apply. So we have a part around our ionic sites where we do stuff to the wave function, and then we have an interstitial part where we commonly represent the wave function exactly. So that is sort of depicted here. So the essence of the PIW method is that we represent our true orbital in two different bases. And so we have a part, and that is, well, this is this psi tilde. This is called the pseudo part of our orbital, of our PIW orbital. this pseudo part is expressed in plane waves. And then locally in spheres around our atomic sites, we use an additional basis, and that is this. These are localized functions that are not expressed in plane waves. They are expressed on radial grids, on radial logarithmic grids. And there you can retain the nodal structure, because these radial logarithmic grids, there you can represent very fine features without too much computational effort. So this pseudo part that is expressed in plane waves, that doesn't contain nodal features. They are sort of being brought back inside spheres around the atomic sites. And these localized functions, essentially how much of these localized functions we admix to our plane wave solution is determined by a projection of our plane wave solution onto a projection operator. So these functions, they're called the partial waves. These are the all-electron partial waves, the pseudo-partial waves, and the PIW projectors. These functions we compute beforehand. So they're stored on these potential files. Yeah? The variational quantity, so for which we will actually solve the equations, are these plane wave parts. So in that sense, we augment this plane wave with these localized functions. And what that sort of ends up with is depicted here. So this is our pseudo-orbital expressed in plane waves. Apart from a zero at the origin where an atom sits, it doesn't have nodal features. Then we subtract a part, that are these pseudized partial waves that have been pre-computed. We subtract a part, and assuming that this set of functions is a complete basis, that means that inside of the spheres where they live, we sort of cancel out the whole of the plane wave part. Yeah? So we end up with something like this, and then we add a part, and that part is given by these all-electron partial waves, and that carries all the nodal features associated with the true atomic wave function. So this is plane waves. This is plane waves minus these radial functions, minus these radial pseudized partial waves, and this is this particular sum, and where we add these all-electron partial waves. And these guys here, they are pre-computed. Right. Yes?
How do you make sure that the wave function is continuous at the interface? That there's no task? Oh, yeah. How do you make sure that at the interface that they're actually continuous, that they match up?
Well, actually, that is guaranteed because of the relationship between these all-electron partial waves and the pseudized ones. So the all-electron partial waves, and I'll show you examples of this. They are solutions to the radial atomic problem. And the pseudized ones, they match onto at a certain cutoff, they match continuously onto the all-electron ones. So this particular, this minus this, doesn't introduce a kink. Yeah, so you have to be well continuous up to the second derivative. Otherwise, you would have a kink in your kinetic energy, and that would be really, really bad. So yes, so that is guaranteed because of the relationship between these pseudized and all the electron partial waves that make up this local basis. Yes.
Can you comment on the differences and pros and cons between PAW and Gaussian type orbitals?
Whoa.
The requester suspects that for molecules, Gaussian type is better, and for periodic solids, PAW is better. And is there an effort to allow for mixing these types?
No, there is no effort in Vasp to allow for mixing these types. There are other programs that use, I don't know exactly one, that uses Gaussian type orbitals, sort of a Gaussian augmented plane wave formalism, something like that does exist. I do not necessarily agree that it's better to use Gaussians for molecules per se. And I have a slide in the second lecture. There's a slide where we compare against Gaussian description of, I think it is Cl2, so a chlorine dimer, where actually you see that the number, to be really accurate, you see that the number of functions that you would have to include in your Gaussian basis is huge, and at some point it will even be larger than the number of plane waves that are being used there. So because that would be the measure, right? So how large does my basis have to be in terms of Gaussians with respect to how many basis functions do I need here, how many plane waves would I need to use. And the thing is that this POW formalism, these local bases that we use here, they're very, very small. So we assume them to be complete, which is always an approximation because they're really small. And Gaussian bases can get quite large. Having said that, there are excellent Gaussian bases around, right? I mean, people have been using them in chemistry for a long time. So there's very good basis sets around that are known to work well. It is hard to let's say, how to say this, with plane waves, there's a natural way of reaching completeness of your basis set. You simply increase the cutoff energy, and as you increase the cutoff energy, there's a controllable measure by which your basis set becomes more complete. This is much more difficult with Gaussian basis functions. Having said, there's so much effort has been put into Gaussian basis set that there are really truly excellent basis sets around. Yeah, I don't want to knock them, but from a conceptual point of view, there's difficulties there. Yes.
How does this method compare to just the regular pseudo potential methods in terms of computational cost? Because you already have a basis that you can calculate the derivatives already and everything. So
yes. So in terms of this is as expensive as doing a separable pseudo potential. So it is not more expensive than that. So it is a separable pseudo potential. So or ultra soft ones. There's no essential difference. Yes.
So we have 3 minutes to the first break. So
yes.
How we do this?
I think we should do that, and I think that yes. I will simply continue sort of, we'll see where we end today and where I continue tomorrow, right?
Okay.
Yes.
Yeah, so
I mean, I like it, I like the way it is going now with lots of questions, but it might mean that I can't do each and every slide that I've brought with me, but I think that is less important than answering the questions. So I would like to continue as we are doing now.
Okay, so by 10:30, let's have a break anyway.
Okay. That's good. So then I'll squeeze in another slide, right?
Okay.
Okay, so what do we have? We have a plane wave basis for this pseudo part, and then we have inside of what we call the PAW spheres, centered on the atomic sites, we have these additional local basis functions that are pre-computed. So, and these basis functions, how are they computed? They are the solutions to the radial scalar relativistic non-spin polarized Schrödinger equation for the atom. So if I have a helium atom in my system, at some point in the creation of these Podcar files that are associated, these potential files, this particular radial scalar relativistic non-spin polarized Schrödinger equation was solved for the helium atom in some particular configuration. That is written here. And from these states, which are the eigenstates of this atomic problem, and they live on radial logarithmic grids. So from these states, we then use a pseudization procedure to get the relevant pseudized counterparts. So we have eigenstates for this particular atomic problem, and from these all electron eigenstates we can create pseudized versions, we can pseudize the effective potential of the atomic problem, and we can construct these projector functions. And these projector functions, the only thing that we need to ensure is that they're dual to these pseudized states. And there's procedures to do this, how to construct them. I don't want to go into that too much. So which functions do we take into our basis? Well, the natural choices that we make is that we would include all the bound states for the atomic problem, all the bound states of the valence, and not the core states. They're put into this frozen core approximation, but for the valence electrons of the atom, we include all the bound states, and then we compute some additional solutions at some energies a bit away from the bound state. So this yields some additional variational freedom inside of this local basis. For that, we construct these pseudized counterparts and the projector functions. And a lot of the technical expertise goes into making a wise choice for these projector functions. Because if you look at this, the only place where radial logarithmic quantities, and those are those guys, they live on radial logarithmic grids, where they meet is here. And we have to project our object in plane waves onto these projector functions. So these projector functions, they have to be representable in plane waves as well. And everything is representable in plane wave, obviously, but we want to do this with a limited number. Otherwise, we end up with an operation that is prohibitively expensive. So there we have to make a wise choice. And well, that is one of what we consider to be a strong point of our program, is that Georg Kresse has lots of expertise in doing this and has created this set of pseudo-potentials that is quite robust. Because this all applies obviously for the atomic problem, but then we put it into some chemical environment. And the transferability of the PAW method is very high. So if you would ask, how does this compare to other pseudo-potential methods? In that sense, it's incomparable. It's much more transferable. You can take the atomic problem and put it into a chemical environment, and it will still work. Yes?
While constructing the pseudo-potentials, your all-electron part is scalar relativistic and not spin polarized. How does it affect if we want to include the valence level, even include the spin orbit coupling and spin polarized calculations?
Yes, that is a very good question. So this choice of basis, a scalar relativistic basis, how does this affect spin-orbit coupling? It does affect spin-orbit coupling, obviously. So for heavy elements, the spin-orbit splitting is, I think for lead, it is off by something like 10%. Because of the fact that these local functions that you include are not J functions, they're L functions, right? Yes. So yes, that is which one could extend the code to use different functions. Obviously, it shouldn't, for the code, it shouldn't matter what it gets here. So you could work with functions that were created for an equation where spin-orbit coupling was included in some other way, but that we haven't done. And actually, unfortunately, that would be quite a lot of work to include that. If you look at other methods like FLAPW, where you can include local orbitals or things like this is typically what they would include if you go to very heavy elements. There are certain local orbitals they would include because they have slightly more density at the nucleus, and those are essentially relativistic effects that are not covered by our basis functions here. Which doesn't mean that it's not that it's completely absent, because there's always this plane wave part that carries more freedom than what is removed by this particular. So we don't particularly ever reach this situation where this is completely cancelled out. The plane wave part survives partly in this area, and you would say, okay, that is that is a bad thing. Actually, it is a good thing, because some degrees of freedom in your plane waves set, they still survive here, and they help with the incompleteness of these local functions. It's a bit controversial, or not controversial. Well, anyway, it is. So this clean separation where you cancel this out completely, we don't want to achieve that always. There are situations where having the additional degrees of freedom of the plane wave survive in the spheres actually helps you. Yeah.
Okay, let's stop here.
Okay.
So we will resume at 11.
Okay, good.